In this second part on the antiderivative of ax plus b to the power of n video, we're going to look at this integral and this formula that's not on the formula sheet. So if you want to see how to use this formula, go back and have a look at the part 1 video. Okay, so let's move on. Where does the formula come from? Now, if you don't want to watch this, there is an important formula down here. It's in a blue box, so by all means scroll ahead, but make sure you copy down the formula in the blue box. All right, for those that want to know how it goes, the formula works, where it comes from, let's go. So if we take the derivative of log of f of x, what we get is the derivative of the function over the function itself, as long as f of x is greater than 0, because you can only take log of positive numbers. So we have to have positive values for f of x. So if we reverse the process and we integrate both sides, so we integrate this side, we integrate this side, the integral on this side will undo the derivative. We'll get back to this function, see it here, plus our integration constant. So our integral of the derivative over the original function is our log function plus c, making sure that our original function f of x is greater than 0. So what happens if f of x is less than 0? Well, if f of x is less than 0, that means that f of x is negative. And if you take the negative value of a negative number, you get a positive value, which is what this is saying here. Negative f of x is greater than 0. So we could put negative f of x in as our function for f of x. Now, if we do that, what we get, you'll have to trust me here, or you could try it on your CAS calculator, is the negative derivative over the negative original function, and you can see that the two negatives will cancel down to just give us this original formula that we had back up here at the top. And so if we are finding the integral of, if we are finding the integral of f of the derivative over the original function, our answer could also be the negative function, as long as the negative function is greater than 0. So we've got two answers here for the one function. This one here that has the positive f of x values, and this one here that has the negative f of x values. So what we're going to do is we're going to combine the two together into a hybrid function. And you can see that I've got the first function that we had where f of x was positive, and the second function where f of x was negative with our thing here. And then we're going to combine it together. Now, we're going to use absolute value function. So this is the one that I want you to put in your bound book. It's not in your bound book, and it's not in the textbook, but it's a really nice one to have, because this is the basis for the other two formula that we're going to get to in a sec. So if you have the derivative, if you have the integral of a derivative over its function, the answer is log to the base e of that function, but taking only the positive answer that you get here. So this absolute value, or if you study physics, this is the magnitude symbols for f of x, is the f of x value if it's positive, and it's the negative version of the negative answer. So basically, if this answer is -3, let me write this over here. The absolute value of -3 is 3. The absolute value of 3 is 3. The absolute value of -1.5 is 1.5. The absolute value of -2.3 is 2.3. So whatever the size of the answer is, you keep, but you just disregard the negative answer. That's what your absolute value function does. So this will work as long as you can see we've got f of x greater than 0 and f of x less than 0. Now, if f of x is equal to 0, what you're trying to integrate is 1 over 0. You've got a 0 at the bottom. You're trying to divide by 0, and we know that anything divided by 0 is undefined. So there is no integral defined if f of x is equal to 0. All right. Let's have a little bit of practice using this formula, and then we'll develop the formulas that are actually on the formula sheet. Okay, so here are some examples of integrals where we have a function and its derivative. So the derivative of sine x is cos x. So we've got f dashed x over f of x. So our answer is log to the base e of f of x in absolute value functions plus c. Now, on your CAS, it's going to give you this as the answer. A big, massive straight lines and curves. What it's actually trying to show you is that it's the natural log, so log to the base e, of, whole brackets, absolute value brackets, sine of x. So I should probably have those in my purple colour, but they're the absolute value function ones there. The other thing I want you to be careful of, you'll notice that we've got a plus c here, and on your CAS there's no plus c. You have to remember to write that. If the integral that we're doing just has the integral symbol with nothing at the top and the bottom, you have to put the plus c, okay? Don't get tricked by your CAS. All right, so let's have a look at this one. Function, there's its derivative. The integral of that is log to the base e of the function, which is the one that's on the bottom, plus c. On your CAS calculator, it looks like that. There's your absolute value symbols as well. So function, derivative, so therefore it's log to the base e of 2x to the power 2e to the power of 2x, the absolute value of those. So here we're actually going to start to play around a little bit with our log laws, because you're probably screaming at me, why didn't you just cancel here? And my advice to you is, if you can cancel here, absolutely cancel here. But I haven't done it because I wanted to show you that when we get to this situation here, we can still use our log laws. That 2x can still come out as a multiplier at the front here. We get 2x times log to the base e of e, which is just a 1. And I forgot to put plus c on that line. And so you can see that what we get to in the end, 2x plus c, is what we would have got to if we have just taken that integral and done a little bit of cancelling down. So divide the top and bottom by e to the 2x, so you get 1 and 1, so you get the integral of 2 with respect to x. We know that the integral of a constant is just the constant times x plus c, which gets us to exactly what we got the long way. So I've done this here as well again for these last couple of examples here. So function, derivative, the integral of that gives you log of the original function. Bring the 2 out the front, gives you 2 log e to the x plus c plus c. Your CAS calculator will give it to you like that. Again, remember that CAS calculator isn't giving you a plus c. You've got to remember to put your plus c on. Same one here for this one. If we do it without doing any cancelling down, this is the derivative of this particular function. Okay, and so that would give us log of the function. If we did do some cancelling down, so I cancelled down the 6 and the 3 to give me 2x on x squared, and I could even cancel down the x's. That we'll talk about that in just a minute. But we've still got derivative over function, log of the function, same answer. So I've got something a little bit different further down here. Let's have a look at what I've done here. So I've done this version without doing the cancelling, just to show you what I get and what happens, because it's kind of a little bit counterintuitive what happens with the 6 and the 3, and it's got to do with this plus c on the end. So I'll show you what happens. So this is a function, this is its derivative, so we get log to the base e of the function. So I'm going to use my log laws to expand this out now. And what I get, you can see, is when you've got log of something times something, you can write it as log of the first thing plus log of the second thing. And you can see log to the base e of 3 is just a number. It's a constant, all right? So this is a constant. And here we go again with these constants. And I've got plus c on the end, which is also a constant. So I have a constant plus a constant, and that gives me just a single constant. Okay, so you can see here that I've just combined this together to be plus c, meaning a constant. This c doesn't have a value, it can be any value, so it's some kind of constant. Now I'm going to use my log laws to bring the 2 out of the front, and I forgot the plus c on the end. See how easy it is to forget that little sucker. Plus c on the end. And that process works the same for all of your power functions, whatever power function you're doing. And so by that I mean x to the power of n. If you've got your derivative on the top, it's log to the base e of x to the n. The n will come out the front. The n will be multiplying the log. So that will just stay exactly where it is. If you've got some kind of common multiplier at the front of your integral, like I had here, so this is like a 3 and a 6, so this is 3 and this is 3 times 2. What you'll get, if you have a look at how it all falls apart, come on, move over, is you can see that in this one here, the common factor will cancel, and I'm back to what I originally had before. Okay, so that's all very interesting, but that is still not the formulas that we've got on the formula sheet. So let's have a look at those. Okay, so let's have a look. It's not the formula at the start that I had for n is equal to -1, but if we take this setup here and we use our f of x as our linear function ax plus b. So if f of x is ax plus b, then our derivative of that is just a. And so our formula, where we've got the integral of the derivative over its original function, becomes the integral of a over ax plus b. And that is going to give us that, okay, straight up. Now, that's not the formula on the formula sheet either, or the other one that I told you to use either. It's in the book, but it's not the one that I told you. So anyway, let's go back. Let's have a look at this. And you'll notice that this a at the top is the coefficient of our x value. And so it's just a constant. So we can bring this out the front. Okay, the old bring that out the front trick. And that gives us a times that integral is log to the base e of the function. All well and good. And now I'm going to get rid of the a from this side, and I'm going to do that by multiplying both sides by 1 on a times 1 on a, and that brings us down to the formula that I showed you at the start, this formula here. Now, you'll notice that I've got brackets here and the absolute value function and the brackets as well. And in this last one, I haven't got that. You can actually use your absolute value function brackets or lines as the brackets as well. Now, if you are going to do this in the exam, you must draw them as straight vertical lines, straight vertical lines. The only way that this is in fact correct is if this is the absolute value function, or you have curved brackets and you're stating that ax plus b has to be greater than 0. Okay, So the easiest way to do this, the quickest way to do this, is make sure that you've got nice, straight, vertical lines. If it looks slightly curved at all, it's going to be wrong. Okay, so make sure they're vertical, not curved at all. Okay, so let's do some examples. Okay, so here we've got the integral of 1 over, and this is our classic, 1 over 2x plus 3, no power here. So this is n is equal to 1 here. All right, so what we do is we use our pattern. So our power, our a value, let me get this here. Our a value is a 2. So it's 1 on a, which is the 2, log to the base e of the absolute value of the function, plus c. That's it. Next one. So this one is also what you're looking for. The key thing that you're looking for is that there's no power here. That this is just raised to the power of 1, which is what we've got here. We've got a multiple here on the top, a constant that we can bring out the front, a common factor, bring it out the front, and that will give us this. Now remember, our a value is the coefficient of our variable, so in this case our a value is -5. And we have as a constant multiplier out the front, that shouldn't have moved. We have as a constant multiplier out the front 3 times that integral. So our answer is going to be 3 times the integral. You can do that whole 3 times the c thing if you like, or you can just finish your brackets off here at the end and put your plus c on the end. If that makes you feel more comfortable, that's fine. And then just multiply through. Oh. Final answer is there. Let's look at the next one. Okay, so this example here, we've got a function, but this is not the derivative. But if we take 3 over 2 out as a common factor, what we're left with is 1 over x, and this is the derivative of this. So the derivative of x is 1. So this is f dashed of x over x. And so our answer becomes 3 on 2 times log of our original function. Now this is almost in the form of, if it had plus something on the end here, this is in the form of the formula that we've been using before. So let's have a look at what it would look like if it did have plus 0 on the end. Then what I would need to do is I would need to take the 3 out as a common factor, and that gives me 1 over 2x plus 0, which when you put it into the formula gives you 3 times a half log to the base e of 2x plus 0. So just 2x, which you can write like that. Now those two answers look different, so how is it that we've got 3 on 2 log e to the modulus of x is the same as 3 on 2 log e to the modulus of 2x? And the answer is in this plus c thing here, the constant. This allows us to say that these two things are different, because this c value here is a different value to this c value here. It's just some constant, and this is another constant. Alright, so to show you that they do end up being the same, I'm going to apply the log laws here. So I'm going to split this into log to the base e of 2 plus log to the base e of x, and you can probably now see where this is going. So that's what I've got here, log to the base e of 2, that's a constant, log to the base e of x, and so what we end up with is a constant, 3 on, so I'm going to I expand the 3 on 2 out, and this here is just a constant. And when I add that constant to my constant that I get here, another constant, you get altogether a different constant. And they're all called C. Constant. Can't even write. N-S-T-A-N-T. Constant. Okay, so they do end up being the same. Alright, so let's look at some more examples. I won't do this whole thing here for every single example that we're doing. The moral of the story is simplify at this stage as much as you can. And here we are, and that doesn't look anything like what we were working with before. But as I just said, simplify at this stage as much as you can. And so I can write this fraction here as x cubed on x squared, take away 2x on x squared. I can split those fractions. And then simplify by dividing the first one by x squared and the second one by x. Then split the integral into two separate integrals if you like, or you can just continue to integrate the whole thing all together. So I've just split it out just to be a little bit pedantic. And then use your integral pattern for x to the power of 1 here. So increase the power by 1 to make it x squared and divide by the new power. And then this one here, we've got a 2 on the top. If we bring the 2 out the front, we've got the integral of 1 on x that we know becomes our log function. We can combine our two c's together, a constant plus a constant, to just become a constant. And if you think back to, or if you look back up here, if I had have integrated this as one integral, I would have just had a single plus c hanging on the end here, not this one in here. So that goes towards also saying, you know, a constant and a constant is just a constant. And then tidy that up by pulling the functions together and combining the two terms, the functions, pulling the two terms together and combining the constants into one. Let's look at another example. So this one definitely doesn't look like derivative over function, and if you had your CAS calculator, you would just put this in and the CAS calculator would spit it out, the final answer. But we can't do this by hand because we don't actually have a pattern for it. But we can split this into something that we can use our integral patterns on. So I'm not sure if you remember doing this in your CAS calculator, but you can actually get your CAS calculator to rewrite this fraction in its equivalent form as 2 minus 7 on x plus 2. So if you can do this, then go right ahead. If you can do this by hand, go right ahead and just scan down to the bottom of the question and make sure that you got it right. Otherwise, I'm going to go through and show you how you take this fraction here and convert it into this. Okay, so the first step that we're going to do is we are going to write, let me just move that out of the way, we are going to write our denominator as having the same, so let me try again. So this has a 1, this has a coefficient of 1, this has a coefficient of 2. The x here has a coefficient of 1, the x here has a coefficient of 2. We're going to write our denominator so that as a multiple of something, so that we end up with the same coefficient on the bottom as on the top. So what we would get is 2 lots of x plus 2 gives us 2x plus 4. So we've got the first part of the 2x plus 4 here, And if we get it to be the full multiple of what's on the bottom, then we can simplify. And so what I'm going to do is I am going to turn our 2x minus 3 into 2x plus 4 minus 4, so that those cancel each other out, minus 3. And what I'm looking at is I'm trying to create this section here as a fraction over x plus 2, and this section here as a fraction over x plus 2. And what that does is when I separate that out, is that it gives me the ability to, at this stage here, cancel down x plus 2, cancel down x plus 2. And this part here becomes this 2 up here. Can you see what's happened there? So x plus 2 cancels with x plus 2, and that leaves me with the 2 that I had up there. So the idea is that you write it so that your top line contains a particular multiple. So see this 2x here? I wanted to have in my multiple of my denominator a 2x, which means that I needed to put a 2 here. And then whatever came out as a result of that, whatever this was, is what I then added in and took out, so that I could use that multiple to cancel down later. So let's continue on with our work on this. That gives us our 2. We can split it into 2 separate integrals if we like, or we can just integrate from there. When we look at 7 over x plus 2, it's not quite in the right format, but this is 7 times, so it's a constant multiplied by a constant, so we can bring it out the front. Then we can continue on. Integrate both sections, add our plus c's, tidy it all together, and we'll end up with a final answer down here. And our final example takes all of the techniques that we've learned and adds on the extra component of actually finding a unique derivative. And generally these questions all follow the same sort of pattern, and you've done these before with antiderivatives. So given some information about the derivative, so they might give you dy dx equals, they might say the gradient of the tangent, they might say something about the gradient function, but they'll give you some information about the derivative of the original function. Then they'll also give you a point on the curve. They'll give you a point on the curve that you can then substitute into the general derivative formula. So substitute into the general derivative formula to find the value of c. So the sorts of questions that you get look like this one down here. Given that dy dx is equal to 2 on x, and the fact that the point e, 5 is on the curve, move this over so we can see it, find the equation for y. So we're going to use the idea that the integral of a derivative gives you the original function plus your constant, okay, whatever the constant is at the end. And so we're going to set that up using the formulas that we've got, that they've given us. So they've said to us that our dy dx is 2x, so that's going to go in there. We've got our point on the curve. E5 is on the curve, and we're going to substitute it in. So away we go. Substitute it in, solve it using our pattern. So the integral of that, the 2 comes out the front, and we're left with the integral of 1 over x, which gives us 2 log e to the x plus c. We're going to substitute in e5. Please do not be scared of the fact that this is an e. It's just our x value. That's our y value. And so our x value is going to go in here, and our y value is going to be, this is going to be the equation of our curve. So our original function here is going to be y is equal to 2 log e to the modulus x plus c. So that's why the 5 is going here at the front with the e substituted in. We tidy up this section, this section here using our log laws. So log to the base e of e is 1. And so we end up with 5 is equal to 2 times 1 plus c. So 5 is equal to 2 plus c. Our c is 3. So our original equation that we're asked to find is in fact that equation just there.